Hello everyone, today we're going to talk about how to find memory leaks with the Unity Profiler and how to prevent and fix these leaks. Nice to meet you. My name is Lucy. I'm a senior software development consultant here at Unity.
And I'm Brian Taylor. I'm a partner engineer at Unity.
Brian and I are both customer-facing engineers, and every day we see a variety of problems by using Unity. And we help out a lot of customers, but we do a little bit different things. So if we want to put into a medical analogy, Brian's team would be more the general practitioner, where his team and him, they're going to help you out in something that's immediate, but if it needs a little bit more time and investigation, then they will triage the issue and send it over either to my team or the Unity Studio production team for longer engagement. So what my team does, we're sort of the specialists. We look at projects and we try to help you out finding a solution for your biggest bottleneck. I specialize in game longevity and memory. So a little bit safe harbor here. I'll give you like a little second to read it all. This is just a legal statement because we're going to show you a little preview of what's going to happen in Memory Profiler, but it's very little. But just to make sure that we'll let you know that some of the changes are going to not be the last one. So some of the UI might still change. As for the agenda, we're going to talk about memory leaks versus growth versus fragmentation. What are the most causes of memory leaks and what are the solutions? And how to use the memory profiler to dissect the source of leak. And then we have Q&A. So the common causes that we have found the leaks, those are causes that Brian and I have both witnessed while helping out customers with the projects. So let's start with leaks versus growth versus fragmentation.
Yeah, so let's talk a little bit about the difference between memory growth and memory leaks. Memory growth is natural and expected part of an app's lifecycle, so due to loading of code and assets, for instance. But memory leaks occur when memory that's supposed to be freed later is lost and unrecoverable. So in managed runtimes like .NET, memory is tracked and freed with a garbage collector. And in Unity, our runtime also tracks and frees some native memory. But there are instances where neither the garbage collector nor the runtime are able to free memory that we would expect to be able to. And these are memory leaks. So memory leaks are unexpected. The memory was intended to be completely freed and returned to the available pool of memory at some point, but something is stopping that from happening. So these could be dangling references, which are still persisting, which keeps the garbage collector from freeing and returning that object, or the memory associated with an object could be left in a completely untracked state, where the system has no way of knowing that memory is available to be freed and reused. So memory fragmentation is a related concept because it results in unusable memory that we would expect to be able to be used. So when sections of free memory are too small for the size of an entire allocation, that memory cannot be used and must be allocated elsewhere, leading to unwanted memory growth. And the garbage collector in Unity is non-moving and non-compacting, which means that non-contiguous blocks of allocated memory are not rearranged to maximize total available contiguous memory. And as a result, fragmentation can often result from repeated allocations and deallocations. So it's best practice to not mix short-lived and long-lived allocations. And a quick side note on this, that this is expected to change with the move to Core CLR's garbage collector, which is moving and compacting. So sometime in the future, we will get some benefits from that. Let's talk about some of the main culprits for memory leaks in Unity that we often see. Usually these deal around handling events, actions, and delegates, around static references, we see a lot of memory leaks, and then around instantiating and destroying game objects. So first, let's talk about events, actions, and delegates. Let's say you have an object like a game manager, and that publishes an event, and another object subscribes to it, like a temporary UI panel. If you were to get rid of that temporary panel without unsubscribing from the game manager's event, the game manager will still maintain a connection to that panel, even though it's been removed. So this means that the garbage collector can't actually clean up the panel's memory, and this creates a leak. So another potential cause of memory leaks are around anonymous functions. So in this example, when adding an event to the game event manager's on-handle events, a delegate gets added to the game event manager's static list of event handlers. And because this Lambda needs to call a method, in this case handle event, on a specific instance of the script, it captures the reference to that script and creates a reference that you must remove later to avoid a leak. And additionally, you can't easily unsubscribe from anonymous lambdas, such as in this example, so we tend to advise avoiding them. So how can you prevent these types of leaks? So dealing with events and actions, you should always unsubscribe from events when you're getting rid of the subscribing object. So a common and very effective way to do this is to subscribe in onEnable, and then unsubscribe, or in start, and then unsubscribe in onDisable. So that way the subscription is only active while your object is actually active. And you should also be aware of subscribing multiple times. Each subscribe must be paired with a matching unsubscribe, or else references will not be cleaned up completely. And if you're not using monobehavior classes, you can use the weak event pattern. This is described on Microsoft's Learn site if you do a search for the weak event pattern. You can also use the iDisposable interface to implement a dispose call that can also handle unsubscribing automatically. And again, you should avoid using anonymous functions or Lambda expressions for subscribing, and instead prefer named methods to make unsubscribing easy. So another common source of leaks is around static references. Static fields, especially collections like a list or a dictionary, can cause memory leaks because they live for the entire lifetime of your application. So if you were to add an object to a static collection and forget to remove it, that object can never be garbage collected, even if it's no longer used anywhere else in your code. And static references are not reset when you load a new scene, so they can cause memory to accumulate over time, which might not be your intention. So double check your usages of any static fields to make sure they actually fit your use case. And for preventing those, once again, be extremely cautious with static fields. Use them sparingly, only if you think you really need to. And if you must use them, you should ensure that you have a clear strategy for clearing them. For example, if you have a static list of all active transforms, make sure each transform removes itself from that list in its onDestroy method.
And then we have the instantiating and destroying game objects. So you don't really have to raise your hand about how many of us have done here, like instantiating and destroying game object. So that's a really common pattern. I saw some hands, all right. So this is a very common pattern. And I do understand why we want to use it, because we're trying actually to save memory by not having everything at the same time, especially during loading time. However, other than CPU spikes, we also can have a little problem when we're instantiating and destroying game objects really often, because that can lead to fragmentation. But the real leak is when the destroyed object will continue to hold references. So we want to show you how the leaks will appear in the memory profiler. So for this, Brian and I have created a very, very simple sample game where we just recreate a shooting scenario where we just have one game object shooting other game objects using this function called shoot. And only this function actually is a cause of major leaks. And let's see why. So what's happening here, we having a public game object new bullet where we're going to put the prefab that will be later instantiated in the shoot function in a local variable. Then we are reassigning it. Don't ask me why, but I've seen that pattern. Then we have instantiating the new material in a local variable as well. Then we are reassigning the material using .material. Then we are adding the game object prefab to a static list of game object, and then invoking an action delegate. Then eventually, we destroy the game object. So why does this create a lot of leaks? Because the new material local variable will still exist because we have destroyed the game object, but we haven't properly disposed of the material. We also have created an allocations every time that we use .material. So .material does not cause leaks, but it does cause an allocation every time you call it, no matter what. And then we are adding the game object in the static list, but we don't know if that's being cleared elsewhere, so we have no control. That's dangerous. Same with the action delegate. So how could we prevent patterns like this for this specific scenario? So I would recommend to separate the logic of the instantiation and the logic of the distraction and the disposing of all the materials and references. So in a separate script, we would have a should with no leaks function, which will only taking care of the instantiation. And then on the instantiated prefab, there would be a script called bullet in this case, where we have like a member variable at the top for the material. Then we have at the start function, we're subscribing to the event. Then in the event, we are instantiating the material first, then assigning it using shared material to avoid the extra allocation, then still adding the game object prefab to the static list, then destroying the game object. So what's different is that on destroy, we also add we're clearing out the material with destroying at the bottom, then we're making sure that we're removing the game object from the static list. And then also we are unsubscribed safely to the event. So we saw that specific scenario, but generally, how do we prevent leaks caused by instantiating, destroying game object? My usual recommendation is don't use it, instantiating and destroying game object. Try to avoid it as much as you can, well, by using either object pooling or even think about some content strategy, management strategy. But if you really, really have to use it, then make sure that you're clearing and destroying all the references, so all the static reference, object, material, textures, meshes, and also to safely unsubscribe all the event, action, and delegate. So let's actually take a look at the memory profiler. So I don't know, do we have many people that they're not familiar with the memory profiler? All right, so I will go, I will do for a quick overview. So when we open the memory profiler, it is a package that we need to install. So it's not going to be part of the Unity engine. And when we open the memory profiler, we see that we have the option of looking at the single snapshot or to compare the snapshot. Comparing snapshot will be allowing you to compare two snapshots at the same time, only two at the time. So when we click on a snapshot, it will actually redirect to the summary. The summary gives us a visual overview of what's going on memory-wise in this specific snapshot. And we have on the top the total resident on device and the total allocated. The total resident is the memory that is actually resident in your application at this moment, and the allocated is the memory, the resources that the OS has allocated for that application. So this memory is not in use yet, but you may be able to use it later. Then we have the allocated memory distribution. If you see, when I'm hovering, it changes color, and the gray out part represents the allocated part of it. Then we have the native, executable, and map, manage, graphics, and track. We'll look at it a little bit later into details. Then we have the manage heap allocation when we have the virtual machine, empty heap space. This represent, of course, like the name recommended, like empty space. So when you see this increase, if you see also like your resident on device increasing, and so does the empty space, that means that you most likely have a fragmentation issue. And then the object memory. At the bottom, we have the top Unity categories, and this actually represents the Unity object that they're using the most memory in this specific snapshot. We can see render texture is the main culprit at this point, and then followed by shader, texture 2D, etc. You may also notice this inspect button that if you click on it, will redirect to the section that you're inspecting. And then over here, we can see the breakdown of all the Unity objects, and you can view it with allocated, resident, or allocated and resident. So the good news is also that now this folder now works, because in the past you were only able to see the allocated. So yay, we got it working now. And well, I didn't code it, but yeah, I'm representing my team for this. And let's actually, okay, let's close this and let's open the render texture. Let's open this. And then we have the reference tree view. So this is not a call stack. This is a reference tree. So we can see all the items that they're actually referencing this given allocation. And then what this allocation is referencing to. Now we're seeing what is referenced by, and then we have this little trick called click, and then boom, everything comes down, which can seem a little bit overwhelming because it's pretty big, but life is overwhelming sometimes. And then, but fortunately, Unity helps you a little bit, because in the information we see the basic with, other than telling you like the allocated native managed graphics, it also will refer to the status. So the status for now doesn't really seem leaked. So there is no really red flag at the moment. And if you need a little bit more information, you will go through the help, which describes that this object, for example, in this case, it was instantiated at runtime, and it also recommends to make sure to use destroy when you want to get rid of it, or unload unused asset call. And this is going to look like the same for the rest. And then let's go to all the memory. We have the graphics, which is just an estimate of the graphic driver and the GPU memory. And then we have the untracked. Untracked memory, like the name suggested, is memory that cannot be tracked by Unity. Why can't be tracked? Because it's memory that's used by third-party plugin, anything malloc, or Marshall alloc H global. So Marshall alloc H global can be freed using free alloc H global, but until we call that call, it's gonna stay in here. And this, then we have the native. Native is anything Unity related. So we have the native objects, which are similar to what we saw in the Unity objects. And then we have the Unity subsystem, where we have the rendering, the managers, and the infamous unknown. This is a bug, we know that. However, we are working on a solution, and we also have something coming up that I will show later that gives us a little bit more information on where these weird allocations are coming from. Then executable and mapped. This is self-explanatory, and then the good old C# managed code, which is strings, int32, etc. Then we have my favorite view, which is the memory map view. So the memory map view will only appear if you're using the single snapshot view. But if you're using that and it still doesn't appear, then you want to click on the preferences, open preferences, and make sure that this show memory map view is actually checked. So why do I love this view that seems a little bit scary? Because we have here the address, the type of memory, allocated native, and the name. This name is actually given by the operating system. This is a Windows build. So if you're using iOS, Nintendo, or whatever, it's going to have different names. So you can see a lot of untracked allocations. So when I have to investigate projects that they have an untracked problem, what I usually do is profile using a native profiler. In cases of Windows, I would use Visual Studio. I would track the memory also with an IL2CPP build, because otherwise the native allocation will not show. So I use that, and I also take a snapshot at the same time with the Unity memory profiler. Just a little heads up, there will be some memory overhead, and if you're low on memory, that may not work because your memory crashes. But if you know that if your memory crashes, you've got a memory problem. And so that's sort of a good news in itself. So then what I would do is compare those addresses to the address that then I found in the native profilers. It is tedious, I know, but to me, it is fun. And an example of like a real-life application was working on a project, had so many untracked allocation, and then I compared using the address and Visual Studio, then found out that an unnamed third-party sound plugin was using a lot of Marshall Alloc H Global. But it wasn't too much the problem of that call, it was also the fact that those scripts were tied to game objects, that they were destroyed prior to the application to be able to call free Alloc H Global. Therefore, it created a leak. And that was fun, actually. It took a week, was long, but it was fun. So now I'm scrolling down because I want to show you also why I like this view. So we have here some fold out in the addresses, and we have different name, Unity or Unity allocator mix. Those are just grouped by Unity and named, I don't know why, but so they're named, for example, here mixed. And we see a bunch of untracked allocation, and then followed by manage heap. Then we see in the name section that there is no name, meaning that the operating system has not named this allocation. So there is a very high chance that those are just empty allocation, that they're contributing to the fragmentation. Those can be also padding up the allocation that precedes it, or those can also be reused. We cannot be certain for sure. However, like I mentioned earlier, if you're seeing your empty object growing and like your resident memory will grow too, then you got a fragmentation issue, and that's where you wanna look at all of the fold-out application and how much empty space you have. And then at that point, you may wanna think about different strategy for allocations. And now let's get back to the juice of the presentation. So let's compare the two snapshots. When I want to investigate a memory leak, what I do, I take different captures throughout the application, and I usually take it before and after a memory-heavy moment of the game. So like in a case of a shooting game, before and after shooting a bunch of enemies, or opening and closing your menu hub, or leveling up, etc. But for this presentation, for the sake of time, we're only comparing the start and the end. So we're going to compare. And then you will see that the memory map view will disappear once this will be opening. It takes a little time, but of course, the higher the memory footprint, the longer it would take to open. So a little bit of patience, which is a good quality. And then we are back on the summary, and already by just looking at it, I can see that there is a growth. I don't know yet if there is a leak, but for sure there is a growth, just we have this visual cue. And we can see that the growth is in the native, if we see the allocated memory distribution, so native and managed. So for native, let's look at the Unity object. Wow, we see 16,476 more new material of, let's look it up, of this type. We can see there are similar allocation size, so most likely it would be the same problem. And then in the reference tree view, this is 0. So like, oh, what's happening? Let's look at the status. And then in the status, we see that this is a leaked dynamically and build time created assets. So, okay, this is leaked. We know there is a leak. And in the help, the Unity profiler will tell us also like how this was created, so by using new material, and that the object that created this doesn't exist anymore. Therefore, this is going to be leaking. So I'd also suggest you like, hey, call destroy on those, and also say to call resources.unload unused assets, which I do recommend to use it sparingly because it is a very taxing call for the CPU, and also it does create a memory map, a map of the memory that needs to be clear, so in case you're low on memory, it might crash the application. And as I said, those are similar size, so safe to assume that this is the same culprit. So if I would need to fix this issue, I will go into my IDE of choice and then make a search of anything that's using new material. Then since we see that reference to this shader, most likely when I instantiate it, I also instantiate it with the shader. That's another queue. Let's look now at all of the memory, which will, oh, yeah, all right. So we have native that matches what we saw. Also graphics, because graphics can also include all the texture, render textures, meshes, etc. So it matches, and then manage. We see that there is 80,541 allocations. Well, we only had 23 at the start. So let's look at what happened. So we have actions. If you remember in my code, I did invoke an action, and we're going to see it here. Then we do again the click of Alt, click, and unfold everything, and we see that there is a game event manager static. So when we invoke that function, that action, it was holding a game event manager. So if I was going to investigate this, again, I go into your IDE of choice, look for anything that matches the name. Then also here we notice that the allocations are of similar size, so we can safely assume that this is the same, but we can check it more, and that's going to be the same. Then we want to see a bullet, my delegate, so let's click here. We can see that, oh, we have a little bit more queue, we have bullets, so there is some reference to another class. Unfold everything. And this bullet class still hold the reference to the game event manager. So again, search every game event manager and then make sure to dispose it properly. Let's look also at the reference to. When we see the reference to, we see that the bullet, it's actually marked as leaked managed shell. So what does it mean? When Unity has a native object that has a managed reference, Unity will create a managed shell so that the managed reference can access the native counterpart. And if the native part is destroyed, still holding the managed reference, then the managed shell will be leaked. So this actually gives us another cue, because if we actually just go into the search bar and just type leaked, then we will slowly see that all of the managed objects, that they are marked as leaked managed shell. So we see that we have a lot of them in both bullet and the game object. So this proves that the game object was destroyed and had the managed reference still on. And this is all for the memory profiler. So that was fun, but coming up in the memory profiler, so I mentioned earlier about the unknown bug. So starting from 6.3 beta, we have added console info to figure out a little bit what's going on. First thing first, we have renamed unknown to unroot because it's a little bit more appropriate name. And also make sure that you're using memory profiler version 1.1.9. So what we added is mem labels, which can contain root information. And also we're looking at exposing the API to specify mem labels also for unsafe utility allocations. And this is roughly how it's going to look like. Right now, this is testing stage, but it will probably look similar. We don't know yet. And then we have seen how powerful it is, the memory profiler, to look at all the memory leaks, mostly the ones caused by Unity itself. However, when coding and multi-threading, it can be really, really difficult, if borderline impossible, to figure out the root cause of leaks caused by multi-threading. So in cases like this, like my grandma used to say, prevention is better than the cure when you're coding with multi-threading. So gotta watch out for best practices.
Yeah, so when dealing with multi-threading, oftentimes in Unity, that's going to be around the job system. So when you're using the job system, the primary source of memory leaks, it deals with native containers and not disposing of them properly. So when you're allocating native containers, you have to provide an allocator type, and this will have implications for how to manage those containers. When you're using allocator.temp, which is meant to last only for a single frame, Unity will automatically dispose of containers with this allocator, so they're not generally a source of memory leaks. Allocator.temp job is for allocating containers that will last for the duration of a job, typically less than a few frames. If you don't dispose of these containers yourself, Unity will eventually clean them up and log a warning message, except in release builds. And while Unity eventually cleans up these containers, you should handle them yourself because they're still considered an actual leak. And allocator.persistent is the most likely culprit for leaks, since it's memory that Unity will not clean up automatically at any point, and you're fully responsible for disposing these containers yourself. So you should ensure that your control flow always allows for dispose to be called when appropriate. It's not very good practice to put them behind like if statements and different control things that might not be called. So often useful to use try finally blocks to make sure that those disposes will be called. And when you're using the job system, you can also schedule dispose calls using the job handle dependency property. And those will automatically dispose those containers when those jobs actually finish. And you should make sure that you are looking for and paying attention to the debug diagnostics and warning messages while running in the editor and in debug builds, as this is where those temporary allocations that are not being disposed will actually show up.
And we have our good old C# thread. So make sure to use concurrent queue actually versus queue or list, because queue or list are actually not thread safe, and this can cause thread contention and a lot of the awful thread problems that you have probably seen in the past. And then avoid the fire and forget. So make always sure to either time out your thread or also to have cancellation token. And also we recommend also using libraries like Poly to build resilient code. But this is a big topic. So if you're interested, register for the webinar. My coworker and I will have a webinar in December 11th, where we will go deep in how to use multi-threading, so the differences between job and C# thread, and how to use which and when. And while I give you the chance to register, I want to give a huge shout out to Martin. Martin Schmidt is our senior software development, no, actually he's a senior software engineer, sorry Martin, and he is responsible for a lot of the fun changes in the memory profiler, and also he was crucial to bulletproof the content of this presentation. Thank you, Martin. And did you all register? Awesome. So to wrap up, now you know the main causes of the leaks, so keep an eye on them when you're developing. Always profile. I have been in crunch time too, so I do know that taking time to profile sometimes is not really ideal. However, if you integrate profiling in your development cycle and start profiling from early on, you will avoid a lot of problems later. Then when you see that you have a leak, make sure to search for a leaked shell, and then watch out when you're coding in multi-threading. And thank you, and any question, we'll be happy to hear and answer.